So just to help everybody remember what we have covered so far. So in this class, we first try to give you some review or background introduction about asymptotics. We talk about asymptotics without random variables, right? That's the basics. And then we start talking about random variables. And we said, oh, the convergence of a random variable sequence is different from the convergence of a real number sequence because we need to define the convergence in what sense? Since each in the sequence, every variable can take random values. So then we talk about the four modes: the almost sure convergence, the convergence in probability, the convergence in the Rth mean, and the convergence in law. And so we define each and try to explain their differences. And then we started talking about some special properties about the empirical CDF, right? The empirical cumulative distribution function and its relationship to the population CDF. How does the convergence work? And we told you that in addition to what we have from the strong law of large numbers, which will tell us that at a given value, the empirical CDF will converge to the population CDF at that value almost surely. In addition to that, we can also have a sort of uniform convergence almost surely. And that's the Lindeberg-Feller Theorem we told you last time, right? And with that, we also talk about, then we move on to talk about some interesting results about the convergence in law. And the first basic we talk about is the Lindeberg theorem, which gives us the equivalence between convergence in law and the convergence of the expected value of some function g applied to the sequence, converging to the expectation of the same g function applied to the random variable limit, right? And then we said that each equivalent statement is about a certain class of function g. And then we said, based on Lindeberg, we can prove the Levy's continuity theorem, which is about the equivalence between convergence in law and the convergence in characteristic function. And that's exactly what we use to prove the central limit theorem for IID, random variables, or random vectors. We talk about the d-dimensional things, right? So that's what we are at. After talking about the central limit theorem, then we want to make the result more general. So our first relaxation is to drop the identical distribution assumption, but just keeping the independence assumption. And that's what we started last time. We call that the Lindeberg-Feller theorem, right? We give you the result and we give you the condition called the Lindeberg condition, which is a sufficient condition to guarantee that even though you don't have the identical distribution anymore, but under that condition, the average or the sum of the independent random variables still satisfies the asymptotic normality. So that's something we're going to elaborate and talk more about today. So after the Lindeberg-Feller theorem, the next result we're going to tell you is that now we have the identical distribution, but we're going to drop the independence. What if we have a sequence of random variables that have some sort of dependence? And under what condition can we still say their average or the sum satisfy the normal asymptotic normality? So that's the other way. So in other words, for this part of our class, we are going to concentrate or focus on the asymptotic normality that we use a lot in our practice. So for example, today, after seeing the Lindeberg-Feller theorem applications, one application will be about to show that, oh, in the linear regression, then simple linear regression, then the coefficient estimate, what we call the beta hat, that estimator actually has asymptotic normality. And that's something we use often in practice, but today we're going to show it that Lindeberg-Feller theorem can give us that result. Okay, so that's all I want to say. Maybe I'll try to, do we have questions for now? If not, I'm just going to pause the recording for a while and then. Okay, so now our camera is back on. I will start our lecture. So we may end our lecture a little bit later than usual because we have to make up the time. Okay, so But if you have to leave, please feel free to do so because we'll have the recording anyway. So let's continue talking about the Lindeberg-Feller Theorem. So the setting we have here is that we still have n goes up. So from 1 to n and go to infinity, right? We still have the sample size goes up. And for every sample size, we have a sequence. So we have one random variable when sample size is 1. We have two random variables when the sample size is 2. And we have n random variables when the sample size is n, and so on. So that's the setting. And here we are just trying to be more general so that it's not necessarily that as our sample size goes up, we still keep the same random variables. So like we don't require x21 to be equal to x11, although we can, but that's not a requirement. We just say that as our sample size goes up, we have the corresponding number of random variables in the sequence, and we are interested in their sum, the sum of the sequence. Okay, so let me switch to this. And so to answer this question, what we try to do is to, and of course, in this Lindeberg-Feller theorem, we have some assumptions. So here, the assumption is that we assume each random variable has mean 0. And we also assume each random variable to have its own variance. So please note that we can always achieve this mean 0 requirement by subtracting its expectation from the random variable. So we can create a mean 0 random variable. And we also assume independence. So everything here is independent. Independence is the strong assumption here. And what we are interested in is the sum for every row. So for the first row, we call that Z1, second row Z2, and Zn here. So we're interested in those sums. So in other words, Zn is defined as the summation of x and I go from 1 to n. And because of this independence, we are able to write the variance of the sum, covariance Zn, just as the sum of x and i's variances. So we will have this. And we give the sum of variances a notation. We call that Bn squared. That's what we talked about last time. So please note that this is a square, right? So variance has a square. If we want to talk about the standard deviation of Zn, then it's Bn. So what we're interested in is when does this normalized Zn, because Zn also has mean 0, that is implied. This is known. Then when does Zn divided by its standard deviation Bn, would it converge in probability, sorry, in law, converge in law to standard normal? That's our question. And the Lindeberg-Feller theorem gave us the sufficient condition. Condition is what we called the Lindeberg condition. So what does it look like? So it basically is 1 over Bn squared times the summation. I go from 1 to n, the expectation of each x and I squared under a truncation times the indicator that the absolute value of x and I is greater or equal than epsilon, any epsilon positive, times Bn. This thing must go to 0 as n goes to infinity. As n goes to infinity. So in other words, and this must hold for every positive epsilon. So what this basically says is that given any positive epsilon, we look at this threshold, epsilon times standard error, right? It could be standard error, by the way, it's the standard deviation of Zn. And we look at, so for example, if epsilon is 1, then it's 1 standard deviation of Zn. We look at each x and I in the summation and see if its absolute value is greater than this threshold, right? If it is, then we count its square inside this expectation. Otherwise, we don't count it. We just put it to 0. So in other words, you can see that if we enlarge this epsilon, fewer x and I squared will stay in this expectation. And then we can expect that this term will become smaller. And so it's more likely that this ratio will go down to 0. But if we shrink the epsilon towards 0, then more x and I squared will stay here. And then this term will be closer to bn squared. Because if we don't have the indicator, if we delete the indicator, don't do the thresholding, then the summation of epsilon x and I squared is exactly bn squared. Then this ratio becomes 1, and it will never go down to 0. However, as long as we have a positive epsilon, then what this says is that this summation is always negligible compared to bn squared as n goes to infinity. That's what we mean. So essentially, what this says, it means that among this bn squared, right, the contribution made by large x and I squared, right, large is defined by this. The contribution made by those large x and I squared is negligible. In other words, we can intuitively think this says that no term x and I squared is dominating the total variance of the sum of the Zn. So basically, the Lindeberg condition says if we have random variables inside the sum, and these random variables have almost equal contributions to the variance, and then we would have this asymptotic normality for the sum without a problem. But if we have some large terms that dominate this variance, then we would have a problem. So that's what intuitively it says. Okay, so we just said that this is the sufficient condition. Is it necessary? That means if we have this convergence in law, does it imply the Lindeberg condition? And the answer is no. So the convergence in law alone cannot imply Lindeberg condition. However, if we add another condition in addition to this convergence in law, then we can imply the Lindeberg condition. So the other direction. So how about if we have convergent law to standard normal, we need another condition. And this is it. 1 over bn squared times the maximum if this goes to 0 as n goes to infinity. So in other words, among the n variances of x and I, we pick the maximum. If this max variance over the total variance is negligible, then together with this condition of convergence and law, we would have the Lindeberg condition. So basically what this says is that the Lindeberg condition is not necessary, only sufficient. To make us go back to Lindeberg condition, we need to add another condition. And also one thing I'm not going to prove, but it should be obvious, is that if we do have the Lindeberg condition, we should have this. So in other words, what I want to say is that these two together goes to Lindeberg condition. However, Lindeberg condition alone can go to this. So Lindeberg can imply this condition, and Lindeberg alone can imply this condition. And that's very interesting. So this implies that Lindeberg is very strong. And why does it imply this, right? The reason is because of this any epsilon greater than 0. So I can find the epsilon so that I will only keep the maximum here. So then that maximum is the max there. So it should still go down to 0. Okay, so for this class, we are not going to prove the Lindeberg condition, so prove the Lindeberg-Feller theorem. The references are given in the notes. So if you're interested, you can check it out. So to see why this Lindeberg condition can give us this convergence in law. And still, we are going to use the continuity theorem as the tool. So now we're going to show you several applications of this Lindeberg-Feller theorem to see that, yes, it can give us very interesting results. Okay, so the first example is very general, I say. And the later example for the regression coefficient estimator is a special case of this. So here we are going to start with IID, random variables. These are IID and one-dimensional. And they all have the mean mu, we denote by mu, and variance sigma square, that's finite. And now we start to create our triangular sequence here. So let's say that we define x and I as some constant z and I times xi minus mu. So you see, by this construction, we would have satisfied the Lindeberg-Feller condition. You see, because we subtract the mean, the expectation of x and I would be 0, and the variance of x and I would be equal to this constant z and I square times sigma square, right? Okay, and using the same notation over there, if we're interested in the average or the sum of those z, x and I, so the Zn by our notation, summation of x and I from 1 to n, this will be our Zn, right? And then what is that? Actually, it's just this z and I times xi minus mu by definition. And the bn square, right, by our definition, is the variance of Zn. And in this case, it will be the summation of those. And this common sigma square can come out. And I will have the sum, I go from 1 to n, z and I square. That's my bn square. Okay, so now we are going to show that for this example, we're going to show that if we have the maximum, again, I from 1 to n, this z and I square, among the n z and I square, if the maximum divided by the sum of z and, okay, just trying to use another notation. Z, I just call this z and j square, j from 1 to n, another index. So if this maximum over sum is going to 0 as n goes to infinity, then we would have Zn divided by Bn converge in law to standard normal. So we are going to show this result. So in other words, in this example, we start with IID, but then we scale each centered IID by this scaling factor Z and I, right? This could be large for some i's, small for some other i's, right? And then we are going to show that under what condition of those scaling factors do we still have the sum with asymptotic normality. So this is to say that the max compared to the sum must be negligible. So again, no term dominates. And to show that, we're going to use the Lindeberg-Feller theorem. We're going to show that this implies the Lindeberg condition. And by the Lindeberg condition, we have the asymptotic normality. That's the idea. Okay, so we're going to just use this example to show you how can we actually prove the Lindeberg condition holds in this exercise. All right, so I'm going to erase this part, but we are going to write this again. So this is the Lindeberg condition. Okay, so we are going to show the Lindeberg condition holds. All right, so let's first start with what we have in the conditioned ratio. For any positive epsilon. Okay, so let's try to simplify this term using the setting here. So we have the Bn squared as sigma squared summation Z and I squared. All right, and also we have the X and I squared by definition. Z and I squared and xi minus mu squared. That's my X and I squared. Okay, and for the indicator function, also by the definition of X and I, it's actually xi minus mu greater or equal than epsilon times Bn divided by Z and I absolute value. Yeah. Okay, I'm just rewriting this condition based on our definition of X and I. Okay, so here is the key. You see that to simplify this condition, and I just need to show this condition going to 0. And it's sufficient if I can show some upper bound of this condition going to 0, because this condition is non-negative. So if it's upper bound going to 0, itself will go down to 0. And to show the upper bound, one way to do it, I have this summation of Z and I squared here, and I sort of have the summation of Z and I squared here, but I can only do that if I can have this term goes out. So I have the summation of Z and I squared. But what hinders me is this indicator function. So what I really want to do is to make this indicator function actually independent of I, irrelevant to I, then I'm good. So what can I do? So you see, in order to do that, I would need to basically, so maybe I should say that to get this thing out, I can already do it because Z and I squared is a constant. I can move it out of the expectation already. Okay, so I have expectation this. So I only keep the random things, random variables in the expectation. But right now, you see, I want to make use of the fact that x1 to xn are IID. So if it's IID, I can replace xi by x1 because they share the same expectation. However, what hinders me is this. This thing also depends on I, and it's different for different I. If I can change this thing to be something not related to I, then you see, I can use the IID property to just make this as x1 and x1. And that can simplify the things. Once it's x1, I can move it out of this summation. So I would have a sum just of z and I squared, and that can be canceled with this. So then how do I find the upper bound? So this thing it's not dependent on I. I can take the maximum. Okay, that's the key. So you see, because I can have this z and I for any I is less or equal than the max. Right? This is by definition of the maximum. Then you see, if I do epsilon bn, this will be greater or equal than okay. And then you see, because this is a lower bound of that, so whenever this holds, this indicator takes value 1, then replacing by this, I will also have an indicator taking value 1. So in other words, what I mean is the indicator of something greater or equal than this, okay, must be less or equal than the indicator of something greater or equal than this. And then I have an upper bound. So the upper bound is okay. And in this expectation, I just copy the above line, but inside the indicator, I'm going to replace by the maximum. Maybe I'll just change this to J so you don't confuse the index. Okay, so you see with this, then I is only in the random variable. And then what I can do is I can safely change this xi to x1 because of the IID. Okay, IID place here. And because now I don't have I in this anymore, I can get it out of the summation. So now you see, I have a very nice cancellation here. So this and this can be canceled. Okay, so then I'm left to show that this upper bound will go to 0 as n goes to infinity. And how to show that? Okay, so one thing we can look at this term, right? We are very close there. You see, our condition is the max z and I square over b, and this is actually bn square, right? If we have the sigma square there. So if we multiply this by sigma square, the sigma square can be canceled. But if you look at here, we actually have this bn square here. So essentially, you see this term, bn, oh, okay, so over the max j, z and j, right? This is what we have. And if we take the square of it, we actually have bn square and max j, z and j square, because the max is still the max square, right? They correspond to each other. So for this one, what we know from over there, and Bn squared by definition is the sum Zn squared times sigma squared. Right? So by the condition, what do we have here? That is going to 0. And we know this is going to infinity because it's just the inverse here times the sigma squared. So by our condition, so if we call this as condition X, this will go to infinity, positive infinity. And this is just a real number sequence, so no randomness involved, right? We just have this convergence. But then what does this tell us? Right, realizing this part greater or equal than is going to infinity, and x1 minus mu has what? It has finite variance. So intuitively, we should know that, oh, because this sign is infinity, going to infinity, so this indicator function will converge to 0 for sure, right? Almost surely we're going to have that. And then we're going to have this thing inside expectation going down to 0, almost surely. But we already know that almost sure convergence to 0 doesn't imply the expectation of that will converge to 0. We still need something to guarantee to go from almost sure convergence to expectation convergence. And we talk about monotone convergence theorem, dominated convergence theorem, and the dominated convergence theorem will apply here. The reason is that what's inside the expectation can have an upper bound random variable, and the upper bound random variable is exactly x1 minus mu squared because the indicator is 0 or 1. So therefore, this x1 minus mu squared is an upper bound of this, and x1 minus mu squared has finite expectation because of this finite variance. So we're done. So just to try to connect what I said, so because of this, since we have this, then we would have x1 minus mu squared times the indicator of x1 minus mu greater or equal than epsilon bn time divided by the max j from 1 to n, absolute value z and j. This random variable sequence converge almost surely to 0 as n goes to infinity. The reason is because this thing is going to infinity. So the indicator is converging to 0 almost surely. And also, this thing, we know, so this term, we know it is greater or it's less or equal than x1 minus mu squared because of this indicator function. And we have the expectation of x1 minus mu squared equal to the variance sigma squared, and it's finite. Because of those, then we have by the dominated convergence theorem, short as DCT, we would have the expectation of this thing. So let me just give it a symbol because it's a really long expression. So let's just call this star star. So this star star is less or equal to that, because then by the dominant convergence theorem, we would have the expectation of the star star going down to 0 as n goes to infinity. Okay. So once we have the expectation going down to 0, we have proved here That is the upper bound of the Lindeberg theorem, the Lindeberg condition, left-hand side is going to 0. And then we have the Lindeberg condition holds. And then we have the asymptotic convergence by the Lindeberg-Feller theorem. So basically what we're trying to show is that this condition is stronger than the Lindeberg condition, and it implies the Lindeberg condition. So that's why as long as we can show the Lindeberg condition holds, then we're good. So I hope this makes more sense to you regarding how we can use this condition. And just for your information, so the technique I use here to obtain an upper bound is actually pretty common. So you're going to see that we're going to use this again when we talk about the coefficient, the regression coefficient estimator. Okay, because here the z and I can be any constant. So you can see that this is a very direct modification so that we are not restricted to just the sum of IIDs. And here, the x and i's are not IID, even though they are still independent. Okay, does that make sense? Okay. All right, so this is the Lindeberg condition. And one thing I want to give next is a stronger condition that implies the Lindeberg condition. And it has a simpler form. And in the cases where you can easily verify this one, you don't have to verify the Lindeberg condition to prove asymptotic normality. So this is called the Lyapunov condition. So what this says is that the condition says that there exists some delta positive such that we have 1 over Bn. We have the power not just 2, but 2 plus delta. So greater than 2 times the summation 1 from 1 to m. Now we have the absolute value of x and I also to the power 2 plus delta. So if we can show this goes down to 0 as n goes to infinity, we satisfy the Lyapunov condition. So you see what we're doing here. First of all, compared to the Lindeberg condition, right here, right, we have Bn squared, and inside the expectation we have x and I squared. But what we does is to truncate the x and I to keep the larger absolute values. Here we don't do any truncation, but we raise the power from 2 to 2 plus delta for both the Bn and the x and I absolute value. So what we can show is that this condition, it implies the Lindeberg condition. So if you can easily show that this holds, then you can have that asymptotic normality. And in order to show that, actually, we're also going to use the upper bound to prove the Lindeberg condition. So going back to that formula, the Lindeberg condition, this one, again, summation x and I squared, indicator absolute value x and I greater or equal than epsilon Bn. So for this Lindeberg condition, how can we make an upper bound of it and to create a Lyapunov condition? So one thing you can easily think of is that, so when this term is taking non-zero value, so when it takes value 1, we must have x and I divided by beta n greater than epsilon, Bn greater than epsilon. So that's something that must hold so that this term is not 0. So with that, we would be able to show that because of what I just said, x and I divided by Bn is greater or equal than epsilon. Because of this, so then when I multiply this term by Bn to the power delta, that's what I want. Okay, so because of the condition here, I multiply this by Bn to the power delta. And also, you see, what I can have here is this delta, 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 right? So if I do have, then if I multiply this whole term by this, I'm just going to write it down first. To the power 2 plus delta. Okay, so what I really want to say is that given this, and if I divide this to this hand side, so then this will be greater or equal than 1. And this is my 1, this is the greater than. So essentially, I can just multiply by this, and I have an upper bound. So because I want the indicator to hold, and that's why I have it. So I have this for every x and I that has this indicator equal to 1. Okay, so with this, then what else? You see, a very natural upper bound is that I just drop the indicator because the indicator is either 1 or 0. So it's less or equal than 1. Okay, I'm here. And because this is for a fixed epsilon, right? For any fixed epsilon, the Lyapunov condition will tell me this will converge to 0. Then I have the upper bound of the Lindeberg converge to 0. So the Lindeberg converge to 0. So that's why the Lyapunov condition is stronger than the Lindeberg condition. And the reason we can do this is by utilizing this fact that when the indicator is 1, we must have the x and I absolute value divided by epsilon times Bn. This ratio must be greater or equal than 1. And as long as this delta is a positive power, then the deltath power is still greater or equal than 1. Okay, so this condition is just introduced for convenience in our applications, because a lot of times you may easily show this, so you don't have to worry about that complicated form in the Lindeberg condition. And we are going to show you an application of this Lyapunov condition right now. Okay, and usually I have to say, you will first try whether delta equals 1 satisfies, because that will be just a cubic. Okay, so let's look at this interesting example. All right, so in this example, the question is, if we have this independent Bernoulli trials, so think about the coin tossing, and let's say that each coin toss has a different success probability. So let's say this. xi, let me do it this way, xi, and they are independent Bernoulli with success probability pi. And the pi's are not necessarily the same. So then the question is, under what condition is the standardized? So which means that we are allowed to do subtraction and scaling, summation of xi. So we do this Bernoulli trial for n times and we take the sum, and under some standardization, will this convert in law to a normal distribution? That's the question we want to answer. Okay, so of course, we know that if the PIs are what? If the PIs are fixed, right? If they're equal to the same P, we can just apply the central limit theorem and we're good. But now the difficulty is that PIs may be different and the PI may even change with n. So we can allow that, right? So basically we can say as we go on the trial, the more we draw, the more we toss, the probability decreases. If that's the case, then we may not have this central limit theorem. So what I'm saying is that if Pi equals P, right, then we have the CLT. So the problem is done. But the Pi now is allowed to change, so then that's different. Okay, so in this case, what do we do? So what we can show is that first of all, let's try to create some standardized or the condition that required by our Lindeberg-Feller Theorem. So now, first of all, let's define this. I'll call that X, maybe I will use the X already, right? So we'll call this as YI, okay, as XI minus PI. So the reason I do this mean deduction is because I need to create a mean zero random variable. Okay, that's what we need for the Lindeberg-Feller condition, Lindeberg-Feller theorem, sorry. And then for the variance, okay, and it's still the variance of xi, right? Doing this shift doesn't change the variance. And we know the variance of Bernoulli is pi 1 minus pi. We know this. So therefore, if I'm interested in the summation, so I call Zn, following my Lindeberg-Feller theorem notation, it's the summation of yi, right? That's my Zn. And then the Bn squared, the notation we use, is the variance of Zn. And it's obvious that it should be summation I from 1 to m, pi times 1 minus pi. Okay, that's all. And so we want to find the condition so that this Zn divided by Bn will be asymptotically normal. So we want to find the condition such that Zn divided by Bn will converge in law to standard normal. Okay, so then let's try to use that Lyapunov condition to find a sufficient condition. And as I said, it's easy to set delta to 1, right? So then 2 plus delta is still an integer. So let's see what is expectation. So let's see, to find the Lyapunov condition with delta equals 1, right? So to do that, we would need the expectation. So here our yi is that x and I. Just try to connect the notations. So we need expectation of yi cubic. And that's what? Because xi is binary, 1 or 0. So we can write the expectation of yi cubic based on the distribution of xi. So with probability pi, xi takes value 1. And then in that case, yi would be 1 minus pi. And we know this is non-negative, so its absolute value is still 1 minus pi to the cube. And when xi takes value 0, the probability is 1 minus pi. In that case, it's 0 minus pi. So yi is negative pi, and the absolute value would be pi cubic. There was a typo in the notes, and I corrected it. So if you re-download the notes from the CCLE, you will see the correction. Okay, so with this, then let's try to combine the terms. Then we would have pi times 1 minus pi as the common factor. And then getting it out, we will have 1 minus pi squared plus pi squared. Okay, and we can easily show that because pi is between 0 and 1. We can easily show that this is always less or equal to 1. So this is less or equal to 1, and this is what? This is what we have inside here. It's actually the variance of yi. So in other words, you see, because of this, then we would have, let me move here. Then we have summation expectation y absolute value cube. This will be less or equal than summation pi 1 minus pi. And this is bn squared. So in other words, the Lyapunov condition is satisfied if we can have bn squared divided by bn cube. If we can have this go down to 0 as n goes to infinity, then we would have expectation yi cube. We will have this go to 0. And this is what we need, right? The Lyapunov. So in other words, we found another sufficient condition for Lyapunov. And Lyapunov is sufficient for Lindeberg. And Lindeberg is sufficient for the asymptotic normality. And so this sufficient condition is actually very simple, because what it implies is that as long as we have bn goes to infinity, we would satisfy this. And bn goes to infinity is equivalent to bn squared goes to infinity. And that's what? That's this. So in other words, this means as long as I have my pi 1 minus pi goes to infinity as n goes to infinity, then I'm good. So what this implies is that as long as my pi doesn't go down to 0 too fast as I goes large, we are good. So clearly when pi is equal to p, we satisfy that, right? Because when it's p,
I just have n times p times 1 minus p, and that clearly will go to infinity as n goes to infinity. But what if you have pi equals 1 over I squared? Then in that case, you wouldn't have this summation going to infinity. So I'm just making an example to understand that to really have this normality for, or normal approximation for the binomial, or this is not exact binomial, sum of Bernoulli random variables, sum of independent Bernoulli random variables, you need this Bernoulli success probability to satisfy. So this condition is not necessary, but it's sufficient. So once you satisfy this, then you can be sure that you will have asymptotic normality for the sum subject to scaling. Okay. So does that make sense? Okay. All right. And so I will skip the next example in our notes. So next example is similar to here, but we are talking about binomial. So it's a binomial. So basically, the binomial is in itself a sum of Bernoulli. But we are going to show that when you have a binomial and the binomial has the p that changes with n, under what condition would you have the binomial to be approximable? The binomial will, after scaling, will converge to a normal random variable. So we're going to skip that because it's very similar to what we discussed here. Okay, so let me see. Finally, I want to talk about that coefficient example. So the regression, because I think that's very related to our practice. But since it's very similar to the previous example where we apply the Lindeberg condition, so I'll go over this very fast because a lot of steps are similar. But I'm just going to show you that the Z and I thing is a general case of this one. Okay, so now let's talk about this least square estimate of a simple regression. So let's say that we have yi equal to alpha intercept plus beta times the covariate xi plus epsilon I and I from 1 to m. This is the simplest model we talk about in the regression class. And here we assume x1 to xn. They are real values and they are fixed. So the random variables here are the error terms. Epsilon 1 to epsilon n, they are IID and with mean 0 and common variance. This is also what we have in the classic linear regression setting. Okay, so now let's estimate beta using the least squares, right? We would have the estimator, least square estimator, denoted by beta hat n. Here we denote the sample size for clarity. This is the formula I think most of us have seen before. Summation I from 1 to n, xi minus the average of x1 to xn, I call that x bar, xn bar, times yi, divided by another sum, xi minus xn bar square. So in other words, this beta n hat is basically a weighted average of the response, yi. And the weights are decided by the covariate. If a covariate is actually farther away from the mean of the covariate, then this data point will have a bigger say in determining the slope, right? We know that. And we actually have the concept called leverage in linear regression, if you have taken a course for that. So this is the beta n hat. And now the question we want to ask is, under what condition would this beta n hat subject to some scaling or standardization be asymptotically normal? Right, so this is of practical interest. Then will tell you that, so the condition, we're going to show that this condition, again, is something we are familiar with. So still here, so you see, this is similar to what we have in beta and hat. In the numerator, we have the max j from 1 to n, and xj minus xm bar square. If this goes to 0, as n goes to infinity, then we would have this beta n hat subject to some standardization, okay, is, I'll say, asymptotically normal. Okay, so again, we're going to show that this is a sufficient condition, and this condition is enough to imply the Lindeberg condition so that we would have asymptotic normality for beta n. So the idea here is that we are going to create some standardized zero mean version random variables so that we can write beta n as the sum of those random variables and subject to some scaling. So that's the whole idea. All right. And also here, the IID random variables are going to be our basis, and they are epsilon1 to epsilon n. So thinking of that, our first step is to re-express beta n hat as a function of epsilon1 to epsilon n. And to do that, you see here we have yi's. So we are going to use this model. Replace yi by alpha plus beta times xi plus epsilon I, so that we will get epsilon1 and epsilon n out. Okay, so first of all, to prove this sufficient condition, the first step we can write is that we can rewrite beta hat n just based on the plugin I just said. We can easily show that is equal to beta plus xi minus xm bar square. Again, xi minus xm bar times epsilon I. So I'm going to show that it can be simplified this way. And epsilon I is IID. We have it and this is not, this is the thing we look at. It's not a summation of epsilon I. It's the summation of epsilon I times something. So that's why it's the special case of the first example we give you. This is basically that Z and I. Okay, so let's say we define X and I. This is the notation in our Lindeberg-Feller Theorem. Xi minus xm bar epsilon I. Okay, so with this, we can have this expectation equal to 0. That's what we want. And variance. Okay, for epsilon I, we know variance is sigma squared. So here we have xi minus xm bar squared times sigma squared. Okay, so basically, if you recall, this is our Z and I, right? So when we show that the sufficient condition in our previous example, we show that, if you recall, the max j, z and j square, summation I from 1 to n, z and I square, right? We show that if this goes to 0, we have the Lindeberg. The same. So basically, you see that condition is just this condition. So therefore, in this example, so same here. In this example, this condition will tell us this will imply the Lindeberg condition. And you know, the Lindeberg condition will actually guarantee that this term, right? This term actually would be asymptotically normal and subject to, right? So here we need to divide that sigma squared so that it's asymptotically standard normal 0, 1. And that's it, basically. So I'm just stop here. I'll stop here and leave you to fill in the remaining gaps, but we're almost there. Okay, so the key is to show that the Lindeberg condition holds. And this is basically the sum of independent but not IID random variables subject to some scaling, right? And you are going to show that what further scaling is needed, so this term will converge in law to standard normal. And then you're going to add back the shift and this, and then finally you're going to show how can we write down the asymptotic condition for the beta n squared, beta n hat. So I can actually write it down for you. I can just show you that essentially we would be able to, so finally for the result, we can show that it implies this. I from 1 to n, xi minus xn bar square times beta n hat minus beta. Okay, this will converge in law to normal 0 mean sigma squared. This is the variance of epsilon I. So this is the result we are going to have finally. And if you want to create the term out, so if you recall in our CLT, right, we wrote this is what we have for CLT. If you want to create a form similar to this one, right, we can also do it. And what we will do, because you see this term increases as n increases, right? So what we can do is that we can write this as root n times 1 over n . That's it. Because this term, you see, this is just the standard deviation of x1 to xn. And we could think about this as stabilizing as n goes large. So therefore, it's basically some root n, same as root n here, times some term that doesn't increase with n, times this difference of the estimator minus its mean, its expectation. This whole term will converge in law to a normal distribution. Okay, so this concludes all I want to say for the applications of the Lindeberg-Feller theorem. So I would say in most cases, we want to find a sufficient condition for the Lindeberg condition so we can achieve asymptotic normality for some statistics that can be written as a scaled version of a sum statistic. And the sum statistic is the sum of independent random variables. And those independent random variables do not need to be identically distributed. Okay. All right, do we have questions for this part? Yes. If we use different delta, and mean if we use different delta, we would have different conditions. Is that what you said? Yeah, exactly. So we're just trying to say that for that Bernoulli example, the previous example, we just found one sufficient condition that can guarantee the asymptotic normality, but that's not for sure, and that's not a necessary condition. Yeah. Okay, so that's all. So because we started late today, so I'll try to finish maybe in 10 minutes by giving an opening of our next topic, is where I said we try to relax the independence to some degree. Then we can do more things. So for today, we're going to just introduce a few concepts as the setup for our next class. Okay, so first of all, we are going to introduce a concept called stationary sequence. So by stationary sequence, it means that if we have a sequence x1, x2, x3, and so on, so xn minus 1, xn, xn plus 1. So by stationary, it means that if we take a subsequence with a fixed length, say this is length 3, k equals 3. And here we pick those 3. So for those length k subsequences, no matter where they start in the whole sequence, their joint distributions will be the same. So that's what we mean by stationary. So the definition says that for any fixed k integer, we would have xi to xi plus k. So that's why I allow k to be 0. When it's 0, then it's just xi by itself. So this will has the same joint distribution, okay, for all I. So no matter where I pick my I in my sequence, this subsequence will always have the same joint distribution. And you can see that the IID is the special case of this. IID basically says this holds for k equals 0. And now we are making it more strong. Yeah. So you see, because of this joint distribution, then we can see that under the stationarity, a natural result is that we would have the covariance of xi and xj, okay, will only depend on the gap. So in other words, I pick x and xj. It could be x1, x3, it could be x2, x4, it could be x3, x5. As long as the gap is fixed, then the covariance will be the same. And that's a result of this joint distribution. Okay, so what does this imply? It basically says, so now I can actually talk about the sample average or the xn bar, even though there may be some dependence. So for example, I could have x1, x2 dependent, x2, x3 dependent. So if I have that adjacent dependency, can I still say something about the distribution of my sample average, just as the central limit theorem? And this assumption is actually very useful for our time series data, where the adjacent time will induce some dependence. But you can safely assume that if the time gap is far enough, then you still have some independence. And that's what we will use next time. But for today, let's take a quick look at the xm bar, the variance of xm bar. Okay, again, by definition, this is so now we don't have independence of x1 to xn, but what's the general form of it? So first of all, we can get 1 over n out as 1 over n squared. So what we know we would have is, first of all, we would have the summation of the variance of xi, right? That's what we'll have for sure. We will also have the covariance for every pair. So that will be I doesn't equal to j from 1 to n, covariance xi, xj. This is just the general formula for the variance of the sum of random variables. Okay, so for the first one, right? So we can simplify it if we assume under the stationarity, right? I said the stationarity will tell me that xi's will have the same variance. So let's say variance of xi, they're all equal to sigma squared. So the first term is easy. I just write as n times sigma squared. For the second term, by the symmetry of covariance, I know the covariance of xi, xj is equal to the covariance of xj, xi. So by that, I can write as 2 times I less than j. I just concede fix the direction of covariance xi, xj. Okay. Now, let me further think about the covariance because we have the stationarity and we say that the covariance only depends on the gap. So now let's look at all the possible covariances by the gap. So let's think about the I minus j if I is less than j, right? And of course, they must be between 1 and n. So think about this gap k. What possible values can I take? So k could be equal to 1, the minimum. So I and j differ by 1. And then how many pairs of I and j would I have? N minus 1, right? So I will have n minus 1 pairs. And what's the largest k? N minus 1. So that's when I is 1, j is n. And how many pairs do I have? Only 1 pair. So in other words, you see, for the gap k, I would have n minus k pairs. So n minus k pairs have gap k. So this motivated me to rewrite the sum by the gap. So in other words, I still keep the 2 here, but this term can be rewritten as k go from 1 to n minus 1. And for each gap k, I have n minus k pairs with the same covariance by the stationarity. So that's covariance x1 to x1 plus k. Because of the stationarity, I can start with 1. Okay, so now you see under the stationarity, if I denote covariance x1 plus k by some notation gamma k, then what would I have? So over here, I would have it as, so let me just write on this side. This will be equal to 1 over n squared, n sigma squared, and plus 2 times k from 1 to n minus 1, n minus k times gamma k. Okay, so just as a reminder, this is the variance of x n bar, sample mean. So let's just do some simplification, and you'll see that, let me see, 2 times that. So you see, now move this inside. I will have 1 over n sigma square and plus 2 times this. Okay, now I have n minus k divided by n squared gamma k. So what I really want to say is, if I have this variance is this, right? And now, so because I want to talk about the asymptotic variance, and I know by the central limit theorem, right? So just look at this alone, we won't get much, because as n goes to infinity, we know this variance, if this gamma k is finite, we know this variance may go down to 0. If in that case, then it doesn't make much sense to say, right? We just have this consistency result, x and bar converging to mu. But if you want to say more about the asymptotic distribution, we look at, again, this x and root times x and bar minus mu, right? So for this term, which we want to talk about asymptotic distribution, then if you think about its variance, okay, so now you see, once you take the root n multiplier, after the variance becomes n. So we will have some cancellation there. So basically, we will have n sigma square plus 2 times k from 1 to n minus 1, n minus k divided by n gamma k. Okay, so with this, if we can show that, okay, this term has some limit. If the question is, does this have a limit, a finite limit? And that's the question we want to address. So next time we are going to show if we only have a finite number of gamma k's to be positive. That means the covariance is only non-zero for certain gap. So let's say the gap less or equal than m, we have the non-zero covariance. After that, the gaps bigger than m will give us 0 covariance. Then we can change the summation to be k from 1 to m. So this summation doesn't change with n. And this ratio will converge to 1, right? So then we will have a finite term here. And that's what we will talk about next time. So basically, we're going to show that with this special type of dependence that only exists for certain gaps in our sequence. And here our x1 to xn have same variance, so identical distribution. So under this case, we can still say something about the asymptotic distribution for the sample average, sample mean. However, here we must have the covariances enter the asymptotic variance in our limit. It's not just the sigma square alone. Okay, so we will stop here and we will continue talking about this next time on Wednesday. And don't forget about the homework due tonight. And also, I will post the good examples about the final papers to CCLE soon, so you can use them as a reference and think about what you want to write. Okay, so that's all for today. Thanks, everyone.